All right, today we're diving into a really incredible story of scientific discovery, all from a paper written way back in 1896. Now, this story has it all: the moon, the mystery of the ice ages, and the very first time anyone ever calculated what we now call climate change. The big question is, how on earth did he pull it off?
I mean, it sounds like something straight out of a sci-fi novel, right? How could a scientist, more than a century ago, with zero supercomputers or satellites, use the moon, of all things, to figure out how one little gas in our atmosphere basically controls the planet's temperature? Well, believe it or not, that's exactly what happened, and we're going to break down how.
Okay, so to really get how mind-blowing this discovery was, we need to rewind the clock a bit. Because before anyone could even think about the future of the climate, they were stuck on this huge puzzle about its past. And that puzzle was the ice ages.
See, by the late 1800s, it wasn't a question of if there were ice ages. Geologists knew for a fact that the world had gone through them. The evidence was, and I mean this literally, carved into the landscape all around them. The real problem was, why? What caused them? That part was a total mystery. They could see the massive scars that these colossal glaciers had scraped across whole continents, from Europe to North America. They did the math and figured that for this to happen, the entire globe had to have been about 4 or 5 degrees Celsius colder. But the question remained, what kind of natural force could act like a planetary thermostat, turning the heat down that much, and then, just as mysteriously, turning it back up?
Turns out, the answer to this massive geological mystery wasn't buried down in the rocks. It was floating right up in the air. Scientists were starting to realize that our atmosphere, this thin layer of gas, acts kind of like a heat blanket for the entire planet, keeping us all warm and cozy.
Now, this basic concept wasn't totally new. It had been floating around since the 1820s. Thinkers like Joseph Fourier came up with this idea that the atmosphere works a lot like the glass in a hothouse. It lets all that bright sunlight stream in, but then it traps a bunch of the heat that tries to radiate back out from the ground.
Okay, so if the atmosphere is a blanket, the next logical question is, what's the blanket made of? What specific part of the atmosphere is actually doing the heat trapping? It couldn't be the big players, nitrogen and oxygen. They're mostly transparent to heat. The real culprit had to be one of the minor gases.
And this, of course, kicked off a huge scientific debate. On one side, you had the brilliant physicist John Tyndall, and he was pretty convinced that water vapor was the most important heat trapper. But on the other side, a lot of scientists were arguing that another tiny trace gas, what they called carbonic acid back then, but we know as carbon dioxide or CO2, was actually the one playing the more critical role in these big long-term climate shifts.
And the reason these gases can do this comes down to a really cool property called selective absorption. Okay, think of it like this. The atmosphere is like a bouncer at a club. It sees the sun's energy coming in, these high-energy light rays, and it's like, yep, you're on the list, come on in. But then, when the Earth tries to radiate that same energy back out as lower-energy heat, what they call dark heat rays, gases like CO2 and water vapor step in front of the exit. They're like, nope, you're not leaving. And that's how the heat gets trapped.
So they had the theory, but proving it, and more than that, actually putting a number on it, figuring out how much warming these gases caused. Now that was the real challenge. And this is where our main character, Svante Arrhenius, gets incredibly clever. He finds the clues he needs hidden in, of all places, moonlight.
I mean, just stop and think about the problem he was facing. It's 1896. You can't see this gas. You don't have fancy infrared spectrometers or modern labs. How in the world do you measure the heat-trapping power of an invisible gas with any kind of accuracy? It seems almost impossible.
Well, this Swedish scientist, Svante Arrhenius, he came up with a solution that was just absolutely brilliant. He realized he didn't need to build a fancy new laboratory because nature had already provided one for him, the entire Earth-Moon system.
So here's how his moonlight method worked, and it's just genius. First, he got his hands on some data from an astronomer named Samuel Langley, who had been carefully measuring the heat radiating from the full moon. Now, the key detail here is that Langley took these measurements at different times, when the moon was at different heights in the sky. This meant the moonlight had to travel through different thicknesses of atmosphere to reach his instruments. And that variation, that was the natural experiment Arrhenius was looking for. By comparing all these different readings, he could start to mathematically tease apart exactly how much heat was being absorbed by the carbonic acid and how much was being absorbed by the water vapor. He could finally calculate their heat-blocking power.
So now he had his numbers, these absorption coefficients. And with this data in hand, he set out to do something that had never been done before. He was about to calculate for the first time in history the precise sensitivity of the Earth's global thermostat.
And let me tell you, this was an absolutely colossal undertaking. We're talking about tens of thousands of calculations. Some estimates say up to 100,000, all done by hand, filling page after page with numbers. And what he created from this mountain of pure arithmetic was, for all intents and purposes, the world's very first mathematical climate model.
And the amazing thing is, his model could actually make specific, testable predictions. For example, he calculated that if the amount of CO2 in the atmosphere were to triple from what it was in his day, the Arctic could warm up by a jaw-dropping 9.3 degrees Celsius. He saw, even back then, that the Arctic was a particularly sensitive region, just like we see today.
He then basically used his model like a time machine, running the numbers for different CO2 scenarios. And what he found was incredible. He calculated that if you dropped CO2 to about half its 1896 level, you'd get between 4 and 5 degrees of cooling, the exact amount scientists figured was needed to trigger an ice age. And if you went the other way and tripled the CO2, you'd get 8 to 9 degrees of warming, which perfectly explained the lush, genial climates we see in the ancient fossil record. It all fit.
And through all this, he uncovered a really crucial rule about how CO2 works. He found that if CO2 increases geometrically, so if you double it, then double it again, the temperature goes up arithmetically, in predictable steps. It's like adding blankets on a cold night. The first blanket makes a huge difference, right? The second one still makes you warmer, and so does the third, and so on. This predictable step-by-step warming relationship is a core principle of climate science that we still use today.
So armed with these groundbreaking calculations, Arrhenius was finally ready to connect all the dots. He was ready to give a real, quantitative answer to that great geological mystery of the ice ages.
And just like that, the puzzle was solved. Arrhenius had found the master dial that could control the planet's thermostat. If you turned the CO2 down, you could explain the deep freeze of the ice ages. If you cranked it up, you could explain the balmy, tropical warmth of earlier eras. It all came back to this one single gas.
But this led to one last, really critical question. Okay, if CO2 is the thermostat, what's the hand that turns the dial? What kind of natural process could cause these absolutely massive swings in atmospheric CO2 over geological timescales? Well, Arrhenius found the answer in the work of his colleague, a professor named Arvid Högbohm. Högbohm had been studying the Earth's deep carbon cycle, and he concluded that the main driver over millions of years was volcanic activity. He figured that long periods of intense volcanism would pump tons of CO2 into the air and warm the planet, while geologically quiet periods would allow natural processes to slowly draw that CO2 back down, cooling everything off.
And there you have it. That was the final piece of the puzzle. Using the faint light from the moon and just an incredible amount of painstaking calculation, Svante Arrhenius had done it. He hadn't just solved the riddle of the ice ages, he established the fundamental, quantitative link between the amount of carbon in the atmosphere and the temperature of the entire planet.
Think about that. He figured out this fundamental connection way back in 1896, at a time when industrial coal burning was, as his colleague put it, just a tiny fraction of the CO2 already in the atmosphere. And that leaves us with a pretty heavy question, doesn't it? What does it mean that we, today, are now testing his theory on a global scale?